When even a Nobel Laureate in physics begins to question our current understanding of the universe, it's clear that cosmology stands on the brink of significant revelations. Adam Rees, while not alone in his perplexity, is one of many scientists who are now grappling with data from the James Webb Space Telescope, JWST, that challenge long-held assumptions. The telescope is uncovering unprecedented cosmic structures that contradict traditional cosmology. But how is it possible that such previously unimaginable cosmic structures are now confirmed? What implications do these discoveries hold for future research? And do they signal that some of our theories may have run their course? One key mystery is the rate at which the universe is expanding. Though this question seems straightforward, it touches on a profound research challenge that has puzzled scientists for decades. It's now widely accepted that the universe has been expanding continuously since its birth around 13.8 billion years ago. This means galaxies are moving away from each other, with the speed of this recession directly proportional to their distance from one another. In other words, if Galaxy A is twice as far from Earth as Galaxy B, it's moving away from us at twice the speed. Edwin Hubble was one of the first scientists to recognize this relationship, and he formulated the Hubble constant, a value needed to calculate how quickly galaxies are moving apart based on their distance. However, determining the exact value of the Hubble constant has been contentious, as measurements have yielded inconsistent results depending on the method used. One method relies on studying cosmic microwave background radiation, a near-uniform remnant from the universe's origin, which supports the Big Bang theory and yields a value of around 67 km per second per megaparsec. In contrast, when astronomers use certain stars whose brightness varies predictably to measure distances, they get a higher value of about 73 km per second per megaparsec. This discrepancy, known as the Hubble tension, remains unexplained, and the JWST is now focusing on this enigma. Some researchers initially thought the discrepancy might result from errors in the Hubble Space Telescope's measurements. Adam Rees, a physicist from Johns Hopkins University and a Nobel laureate for his work on the universe's accelerating expansion, used the JWST to examine possible errors in the Hubble data. To measure the universe's expansion, scientists use what's called the cosmic distance ladder. Each step depends on the previous one, so any potential measurement errors could cascade through the entire process. The JWST, being much more powerful than Hubble, allows scientists to observe more distant cosmic markers with greater accuracy. Yet, recent studies published in the astrophysical journal Letters showed no measurement errors, leaving the Hubble tension unresolved. Rees suggests that the issue might lie in our basic understanding of the universe. Rees and his team are not alone in seeking answers. Scientists at universities like Bonn and St. Andrews propose that our planet could be in a low-density bubble in space, surrounded by regions of higher matter density. The gravitational pull from these dense areas might be accelerating nearby galaxies' movement away from us, contributing to the perceived higher local expansion rate. However, the standard cosmological model doesn't account for such bubbles. Instead, it assumes matter is evenly distributed across space, following Einstein's gravity model. But if gravity operates differently than Einstein theorized, as suggested by a modified model from Israeli physicist Mordechai Milgrom, the Hubble tension might be resolved. Milgrom's model, known as modified Newtonian dynamics, MOND, aligns well with the observed bubble effect, although it's not widely accepted. The JWST is also challenging existing cosmological theories by discovering ancient galaxies with properties that shouldn't exist so early in the universe's history. For instance, the galaxy JADES GSZ 13-0 holds a record redshift of 14.32, meaning it formed just 290 million years after the Big Bang. This cosmic infant defies existing theoretical models due to its brightness and mass, and its formation would have required rapid accumulation of matter, far faster than expected. Alongside this galaxy, the JWST has identified 6 other massive galaxies from a period when the universe was only 500 to 700 million years old. These galaxies resemble modern galaxies like the Milky Way, despite forming much earlier than models predict. Dubbed universe breakers, they each contain upwards of 10 billion solar masses of stars, with one possibly exceeding a billion solar masses alone. Perhaps the theory of the universe's origin itself needs rethinking. Our current understanding of cosmic development suggests that, shortly after the Big Bang, dark matter condensed into massive clusters known as halos. These halos, through their gravitational influence, attracted ordinary matter, eventually forming stars and galaxies. However, this process was thought to take considerable time, as matter would gradually accumulate, creating progressively larger structures. Yet, recent discoveries by the James Webb Space Telescope, JWST, have found galaxies that challenge this timeline, leading many scientists to question existing models. Previous theories do not predict as many dark matter halos in the early universe as would be required to form such massive structures. Despite these findings, some experts are cautious about discarding established theories. Julian Munoz from the University of Texas at Austin, for example, advocates for a careful interpretation of the JWST data. Munoz notes that if there were indeed 10 times more dark matter structures in the early universe than previously believed, there should likewise be far more galaxies in JWST images. However, similar discrepancies were found when Munoz's team analyzed Hubble data, raising the question of which telescope's data is more trustworthy. There is no doubt JWST is more advanced than its predecessor, Hubble, and began its scientific mission in 2022. Hubble, on the other hand, has been observing the cosmos for nearly 35 years, and its data is widely trusted. Munoz suggests that, for now, Hubble's observations may still be more reliable, and that perhaps there are alternative explanations for these puzzling early galaxies that don't require us to entirely rewrite cosmic history. JWST's observations have undeniably pushed the limits of astronomical research, providing insight into the universe's earliest epochs. Its ability to see extremely distant galaxies has illuminated aspects of the universe's formative years that we previously couldn't observe. If galaxies were present and more massive earlier than expected, our understanding of cosmic evolution could be incomplete or even inaccurate. This presents a major challenge for astronomers and cosmologists, as discrepancies between JWST and Hubble observations suggest either JWST is revealing something fundamentally new, or there are limitations in our current theoretical frameworks. Addressing these discrepancies could lead to a paradigm shift in cosmology. JWST's infrared capabilities have also provided new insights into the distribution and composition of cosmic dust and gas, both essential for understanding star formation and galaxy development. By peering through dust clouds that block visible light, JWST has uncovered hidden star-forming regions and galaxies. These observations may require a reassessment of the role dark matter and dark energy play in the universe's structure. Dark matter, detected through its gravitational effects, could have structured the early universe differently than current models suggest. Similarly, dark energy, thought to drive the universe's accelerated expansion, might also need theoretical adjustments to align with new findings. The differences between Hubble and JWST data underscore the need for rigorous calibration and cross-validation of astronomical instruments. While JWST is more advanced, confirming its findings against Hubble and other established telescopes is essential to ensure accuracy. Beyond theory, these findings have practical implications for future space missions. If the early universe was more complex than we thought, future telescopes may need even more sensitive instruments to detect faint signals and distinguish between various cosmic phenomena. These discoveries may also encourage scientists to explore alternative theories in cosmology, such as modifications to general relativity or novel explanations for dark matter and dark energy. The scientific community will need to engage in open, rigorous discussion about the implications of JWST's discoveries. Peer-reviewed publications, conferences, and collaborative research will play crucial roles in analyzing and validating this new data. As researchers work to understand JWST's findings, they must consider how these discoveries fit into our broader understanding of the universe. Reconciling new data with existing theories is a familiar challenge in science. History shows that scientific progress often involves revising, or even overturning, established theories. For instance, the shift from Newtonian mechanics to Einstein's theory of relativity marked a profound change in our understanding of space and time. Similarly, the potential need to re-evaluate our cosmological models in light of JWST's observations could represent a major leap forward in our quest to comprehend the universe's nature and origins. In summary, JWST's findings are expanding our knowledge and challenging existing theories in profound ways. Observations of early galaxies and discrepancies with previous data suggest